so hopefully we're not going to have all this on the board. I'm just going to recap what we were doing last time. So, of course, we're studying Bourgain's circular maximal function, and we're aiming to prove this celebrated theorem that this maximal function is now more bigger than 2. So, to do that, we're going to use a combination of Fourier analysis and elementary geometry. So the Fourier analysis comes in the form of a frequency decomposition of the operator, which is here in my hand, David's talk. So we take our spherical averages, which are given by these convolutions, and we decompose them by forming frequency decomposition. That's involving with these phi j's, where each phi j, okay, it's given by scaling some fixed phi, and the Fourier transform of phi is this little Kelly function, which is supported on a unit annulus. So what I did is I wrote these frequency localized averages into, well, okay, they're given by convolution, and I wrote the convolution kernel in a funny way. So this funny way is to mirror what happens when we don't do a frequency decomposition, but we just do this physical patterning of the spheres, and we're integrating over annuli. So here we're integrating our function against something that looks like a characteristic function of an annulus, but it's got this wiggles which represents some kind of oscillation, so it's a kind of oscillatory characteristic function of an annulus in that way. Okay. So we talked a lot about discretization and duality. And what this told us was that in order to prove a maximal bound, it suffices to prove this kind of multiplicity bound for these oscillating characteristic functions. And here, okay, we have some powers of delta, but crucially, we have to have this additional power of delta, this epsilon p prime, which has to be some positive number. So the role of this is it allows you to sum the frequency. Okay, so when you translate back to the maximal operator, this gives you some gains, j parameters, and get to minus j epsilon. Okay. And then also we discussed briefly the fact that we have an almost L2 bound. Okay. So in particular, we can prove this estimate, which corresponds to taking epsilon 2 to equal to 0. Okay, and this also, to analog, this holds in higher dimensions, but in higher dimensions you get a positive power of epsilon. This is again one of the differences between the 2D and dimensional case. So this is tantalizingly close to proving Bourgain's theorem, because it allows us to prove these frequency localized estimates, but we can't sum the frequencies. So we're just losing by an epsilon. Okay. So all we have to do is nudge this up a little bit to be positive. Okay, so we can't do that at the L2 level alone. It's going to be a little bit more sophisticated, the argument, but the L2 theory is going to help us nevertheless. Okay, so I ended by explaining where this lemma came from. This kind of Cordova style argument where one takes this L2 norm, expands this in terms of the inner products, and then you end up having to look at the inner product pairs between these modulating characteristic or oscillating characteristic functions. And a particular key ingredient was this lemma. Okay, so this improves over the bound one gets in the when we just have regular characteristic functions, because it incorporates the oscillation. Okay, so I stated this, I think, probably in general dimensions. In 2D, okay, well, we didn't have a lemma for characteristic functions in 2D, but it is true in 2D that you have this bound, just this first factor in 2D. If you just have regular characteristic functions. So the gain is really coming from this thing. Okay. So this involves, let's remember what these definitions are. This involves two functions, circle pairs. The first is the distance function, which is just the distance between the centers of the two circles. And the second is the delta function, which is a measure of circle tangents. This is given by a specific formula, which is the magnitude of the difference between the centers and the difference between the radii. Okay? So what is this thing? Well, on the picture here, it's pretty easy to interpret. So here are our two circles. Let's get the big one C1, center x1, and radius r1. And then the little one is C2, center x2, and radius r2. Then it's quite easy to see. Okay, so if we look at the difference between the centers and the difference between the radii, that's going to equal this length. This is not drawn very well. It's going to equal this length. Okay. So if we look at so this is, it corresponds exactly to this length. In particular, this is 0, it can only use the two circles of interior tangent. Okay. So surface can also be exterior tangent, like that, right? But we're never going to be in that situation here because we're dealing with centers that lie in this unit cube and radii about 1. So that kind of excludes the exterior tangent bits. Okay, any questions about all this center? I'm sorry, so much to recap from last time, but they were all on the same page. Okay, so I'm going to talk a little bit about this lemma. I've decided it's important enough to go into the details. And it's also really the key. It's the only Fourier analytic ingredient we're going to use. But of course, it's going to be based on the formula for the Fourier transform of the measure, which will be mentioned in this lecture today. So we write the Fourier transform of the measure as a sum of two terms. Parameterized by signs. So we have in each term an oscillation with frequency given by the normal XC, and then we have radial functions which are our symbols, and they have some specific K, and the K so what we're going to do now is apply this formula into the definitions of these chi's. I'll take the Fourier transform of one of these oscillating characteristic functions. What I'll get, well, okay, we can back out delta. We've got a convolution, so that's going to turn into a product when we take the Fourier transform. And we've also got this translation, which is going to correspond to a modulation when we take the Fourier transform. So, CL. And we've got a dilation of the measure, and then we take the Fourier transform and dilation. Yeah. Okay, so that's the formula for the Fourier transform. Just got to remember that this guy, its Fourier transform is beta function, and we dilate it appropriately, so we get to 2 to the minus j here, which is just delta. Okay. Make sense? So now I'm going to apply Parseval formula, or whatever it's called, linear product. So the linear product of the functions is equal to the linear product of the Fourier transforms. So we're going to get delta squared, and I'm going to saturate out this big linear product. So our oscillatory terms We have e to the 2 pi I x1 minus x2, which would take a conjugate inhibition in the product. And then we have, let's look at these guys. So these guys have a, I'm going to write them out in terms of the formula, maybe I'll include some sums then. So these plus minuses are independently chosen signs. I'm going to have these we're going to have these circuitry terms coming from the formula for the Fourier transform of the measure, and then I have the symbols. The symbols. And then I have the there's a lot going on here. Then I have this beta function. Okay, that's it. Right. Okay. So that's just plugging in the formula to Pascal formula. And now, of course, this is screaming out to use polar coordinates because basically everything here, well, more or less, that is reasonable. Okay. So let's apply polar coordinates. We'll let rho be our radial coordinate, and omega be our angular coordinate. So the only time we see the angular coordinate is here. The rest of the time it's all rows. Together we can A 1, 2, and then B and then go in of the chain. Okay, makes sense. And now this is okay. So the only part of that that's really this thing that's really mysterious is the well, it's not so mysterious. It's integral, but this is just exactly the Fourier transform of the measure on the sphere, evaluated at a specific point. So this is just sigma hat r of x1 minus x2. See that? Wait, what's this r? Rho, sorry. Rho of x1 minus x2. So we can apply the formula again. Okay. There we go. Now, plus minus, and now we're going to have 3 independent functions of sine. And we're going to have an integral now just in rho. We have the phase coming from this thing, which is e to the plus or minus 2 pi I rho times the norm, x1 minus x2. Plus and minus here. And then we've got the other terms, plus and minus R1, plus and minus R2. This is all times rho, okay? So this is just taking the base coming from the Fourier transform formula, combining with these forces. Yeah. And now we have an A of rho x1 minus x2, and we can retransform the substation here, and then build all the other A's, join it. Okay, and then we've got the okay. So at this point, what I'll do is I'll explain where this formula comes from without this extra decay term. And it's pretty straightforward to see. So if we pull in absolute values, okay, we ignore this oscillation, then what we get is the delta squared. So I'm going to remember the decay of all these A's, which is like a 1/2 decay. So I'm going to get the integral over the rows. First, the decay coming from this symbol. And then for the other symbols, okay, this is rho to the minus 1/2. These are sort of not ones, so we don't worry about rho to the minus 1/2, rho to the minus 1/2, and then the Jacobian factor, they all cancel out. So then we're just left with this and this cutoff function. Okay? That makes sense? So this beta, when we scale with the delta, this is living at scale of delta minus 1. Okay, so on the domain of integration, this decay term looks like this. Okay, and then how big is the domain of integration? Well, it's delta minus 1. So we get delta minus 1 for the length of the integration, length of the delta squared from the delta. Make sense? So that, by just pulling the absolute values in, we get this inequality, which is actually a bit trivial because it's what you get if you don't have any, well, as you expect, you don't have any cancellation. But then, of course, to get this term, we just use the oscillatory factor, and we just use repeated integration by parts. Okay? So, the additional delta, okay, and repeated integration by parts. What I mean is we just do the integration by parts at this stage, and this will pull out a bunch of factors that are, well, power of the phase, and then we take the absolute values. Okay. Does that seem reasonable? Now there are 8 terms because there are 8 choices of sign, okay? But if but we can, okay, really there are only 4 distinct choices because, you know, there'll be plus or minus the whole thing. It's just the relative changes between them. And it turns out of the 4, there's only one where you don't get rapid decay always, and that's when we look at this delta thing. And that's related. So one of them, for instance, will measure exterior tangency, but because we're never exterior tangent, you never see that term. So there's only the term that deals with interior tangency that we see. Okay. That's all the Fourier analysis done. Are there any questions about this thing? Okay, so this is the only really Fourier analytic tool that we use in the whole proof. Okay. So this lemma is telling us that we're in a really good situation whenever our circles intersect transversely. Okay, because if they're transversely intersect, then this delta quantity will be large, and then we get absolutely loads of decay. Because it's really isolates the tangent circles with the key end in a very strong sense. So I'm going to illustrate that by proving the following lemma, which is going to be an improvement. We'll keep this for now. It's going to be an improvement on our previous L2 level under additional hypotheses. Plus lambda 1 because the first new lambda in this lecture. I'll call this the transverse fit implies L2 improvement. Okay. So I'm going to suppose we have our collection of circles. So whenever I have a collection of circles, they always satisfy the hypotheses up there. So the centers are always in this unit cube and or whatever, and then the radii are always in this unit interval. And they always have delta separated centers, okay? So I'm going to suppose our collection of circles satisfies the following hypothesis. So I'll call this hypothesis transversal. So if we look at any fixed circle C1 in our collection, and we count the number of circles C2, which are close to being tangent to C1, that means we look at this delta quantity. This is going to be small. How small? Well, the smallest that makes sense, the smallest possible thing to consider would be delta, because that's our minimal scale. I'm going to allow it to be a little bit bigger than delta, so that's the one with eta, where eta is some small value. Okay? So close to being tangent. And we want there to be fewer of these. Okay? So a trivial bound would be delta minus 2. There's delta, at most delta minus 2 circles in the collection if we've got delta separated centers. And we want it to be small, so we're going to beat the trivial bound by quite a lot. So I'm going to use delta to the 2/3 plus 4 epsilon. Okay, so these are numbers that look kind of random right now, and there's a lot of leeway to choose these numbers. And these eta and epsilon are just some fixed parameters. Okay. So then what we can say is that we have an improvement on our L2 value. Particularly, we get delta the epsilon. Okay. So what's this lemma saying? Well, it's allowing us to know our enemy. Because this is saying if there are very few, okay, this transversality hypothesis is the very few tangent circles. Okay. So if there are very few tangent circles, we beat the L2 value. Remember, we only need to beat it by an epsilon, so then we're good. The only case we have to really worry about is when there are many tangent circles. Make sense? And this is natural given what the inner product pairing and how that behaves, yeah? Any questions about the statement? Okay, so let's look at the proof. The proof's not going to be very difficult because it's just using all the ideas that we did previously. So as usual, we're going to take the L2 norm squared and write it in terms of the inner product. And we get a double sum over pairs of circles of these inner product pairings. And at this point, I'm going to partition the sum according to whether we're in a transverse or tangential case. Okay? So first of all, we're going to take some where we first summon C1, and we're going to summon C2, which form a tangent pair with C1. In particular, this delta product is less than delta 2 minus theta. Okay? And then, got the remaining sum, all C2s, which form transverse pair. Delta quantities in that. Okay. And write this all out with these names. So call the first sum sigma tangential, and the second sum sigma transverse. Okay. So first of all, dealing with the transverse case is pretty trivial. So well, here, of course, we're going to get massive rapid decay coming from the lemma. So in the transverse case, we can bound this in a product pairing. But I'm not going to bother with using the whole formula. I'll just use the decay and delta. So we're free to choose any exponent for this decay. So I'm going to choose some big, well, let's say I'll choose 1,000 over eta, okay? And then when I do this, if I plug in this lower bound on the tangency, then of course this is going to be bounded by below by delta minus eta. So then we're going to get this whole thing, which takes into account that power, is less than delta to the 1,000. Okay? And since there are not many circles in the collections of most delta minus 2, that means that the transverse term is going to be tiny, it's bound by so you might not store really minus tiny items, which definitely needed for our purposes. Okay. Happy with that? So this is pretty trivial. So let's go to the meat of the matter, which is the tangent case. So here, we're going to use the hypothesis that there are very few tangent pairings, okay? And that's going to give us our improvement. So to do that, I'm going to apply Holder's inequality. Following. So I look at the tangent contribution. I'm going to bound each term again using the lemma, but because now we're in the tangent case, it doesn't really make much sense to think about this factor, so I'm just going to consider the first two factors. Okay, so we'll pull out the delta. We'll have the sum on C1. Then we have the sum in C2. Overall, C2 forming a dependent pair. And then I'm going to have this 1 plus delta minus 1 and the distance between centers, the minus 1 r. Okay? So what I want to do is I want to make this thing kind of summable in the sense that the sum is bounded independently of delta, more or less. So because we're in R2, we'd like a -2 power vector. Okay, so I'm going to use Helder to lift this to a -2 power. So when we do Helder, okay, I need to go from -0.5 to 2, -2, so I need to raise it by a 4th power. Okay. We're going to do Helder. We're using our corner. Yeah, it's defined K. And then I'm going to get the cardinality of the C2 set to the 3/4 power. Okay. C2. That makes sense? Okay. So this thing, quite easy to see. This is bounded by a logarithm. This is in a sum because we've got sufficient decay. We're not two. I'll just say as given. Whereas this thing, okay, this appears in our hypotheses. So by transversal hypothesis, this is going to be bounded by delta 2/3 plus 4 epsilon 3 epsilon 4 epsilon times delta minus. Okay. So now I need to take the relative. Okay, and then once we've applied these bounds, we've got no longer any dependence on C1, so I'm going to cannot C. So I'm going to combine all these things together, so we get the delta powers. Okay, so we get the log double sum, double quarter. Then we've got this delta power up front. And then we've got the delta powers coming from the transverse hypothesis. They all have to be raised to the 3/4 in the Helder. So this is going to give us 1/2 plus 3 epsilon. And then we have minus 3 halves. Okay. And I've missed something. Have the delta. That's that. We've got the delta from the power up front. And then this becomes a half and raised to the right power. So it's 3 epsilon and raised to the right power. That's 3 halves. And then we just got to count out. And now we're basically good because, okay, let's look at the delta powers. So the 1/2, and 3 halves all cancel. So we're left with the delta to the plus 3 epsilon. We can trade one of those epsilons to get rid of the logarithmic blow-up. So we've got a delta to the 2 epsilon, candidate C. And remember, we're estimating the square root of the L2 norm, so when we take the square root, we get a delta to the epsilon. Okay? That makes sense? So this isn't very deep. I mean, it's just we isolated what the bad guys are from the inner product pairing lemma, and then we're just assuming there are a few bad guys, and then the situation is good. Okay? Yeah, any questions about this? Okay, so now we kind of know our enemy, which is when we've got many of these tangent circles. So let's discuss our enemy a little bit. This is going to dominate. Let's So in any case, is, for instance, that there exists some fixed circle such that the number of circles in the collection which are tangent to our fixed circle beta tangent is large. Okay, that's what this lemma isolates. But if we look at the proof of the lemma, it's actually there's a broader class of we can actually narrow down the enemy situation a little bit. So we're actually interested in the number of tangent pairs. So the number of pairs of circles in our collection, which is supposed to be tangent. Okay, so if we look at the proof of the lemma, when we estimate the tangent case, okay, we're assuming that all these, for every C1 this is small, but we could have an average version because we're going to sum in C1. Okay, so some of these fibers could be for some choice of C1 it could be large, but as long as there's few choices of C1, so we could modify our proof a little bit if we wanted to. So really, it's the total number of tangent pairs that matter. Does that make sense? Okay. So a trivial bound for this is just the total number of pairs. We ignore tangents and thing. Okay, so certainly if we realize this trivial bound, then we're in trouble for the L2 theory. Okay? So it'd be nice if this trivial bound was never realized, but it's quite easy to see it is realized. And it's realized by something called, at least try mini, the cloud element theory. Yeah? So one bad guy. What's this? Well, it's just a whole bunch of circles which are tangent at a single point, more or less, yeah? So if you take any two circles from this collection, they're going to be tangent. So this is a bad configuration. We're not going to get an L2 bound. Yes. So a large part of the argument is going to center around showing that this clamshell configuration is essentially the only bad situation, and then analyzing special properties of this guy. Okay, so that's kind of broadly how the proof is going to go. Are there any questions about this? Does that make sense? So our first goal is to show somehow this clamshell configuration is unique. So what I mean by this is it's the only situation where we can have many tangents and many tangent pairs. Okay, so it's the only bad situation really. So in order to do this, I'm going to introduce some definitions. So given a pair of circles, C1 and C2, like that, we're going to be interested in their tangencies. So we've already just introduced this delta quantity. So remember delta is its length. So I'm going to introduce a another a definition, which is the kind of direction of tangency, which is going to be something I call omega C. So omega C1, C2 is the point on C1 at which the almost tangency occurs. So you can see what that means in this picture here, right? So there's a simple formula for this, which is probably not very helpful compared to the picture. It's just given by x1 minus r1 times sigma function r1 minus r2 times the direction of the vector minus the distance to the center. Okay? So that's this. So notice this is not a symmetric quantity. Okay, this C1 is it's a point on C1 where the tangent occurs relative to C2. If we switch the order, then we'd be looking at this point here. Yeah. So omega C2. Happy with this? Okay, so that's one definition. And there's another definition that involves three circles. Okay. So now we're going to consider three circles. C, C1 and C2. Yes, like this. And okay, so this is C. Then this is C1 and C2. I can define these omega points relative to C. So this is omega C, C1. And this is omega C, C2. Okay. And I'm going to look at the angle between them. And that's going to be our next definition. So this angle is theta. So theta is going to be defined to be an angle C, C1, C2. Okay. Well, okay, so actually, let's just try this. So another way to see this is theta is just the angle between the difference in center. Okay. Right. Any questions about these definitions? Okay, so now the final now I want to talk about, which is going to give us the uniqueness of this clamshell configuration. Statement as follows. So we're going to have a bunch of parameters, beta, rho, and kappa. And I'm going to have three circles. We've got C0, C1, and C2. And I'm going to suppose that they satisfy the following. First of all, C0 and C1 close to being tangent, the beta tangent, and C0 and C2 close to being tangent. Okay? There'll be a picture that looks a bit like this. Yeah. And secondly, this actually doesn't play any role whatsoever in the proof of the lemma. You could drop this, but it's useful to refer back to later on. I'm going to assume that the distance between the centres of C0, C1, and C0, C2 is controlled by rho capital. Okay? Okay. So we'll just assume that, and we've got it won't play any role just for future reference. And then finally, I'm going to assume some relationship between the radii of these circles. So I'm going to assume that the circle C0 has made the smallest radii of the three that are ordered by C, R0, so that's an R2, that's an R1. Okay. So this third condition, okay, so the second condition, in practice, we'll be able to impose it by pigeonholing in the radii, and the third condition is again more or less, well, you can more or less consider things case by case, and in most cases, basically cases are similar to others. We'll just assume this order. Okay. Okay, so then further, let's suppose that C1 and C2 are close to being tangent. So I'll set this in a very specific way. So if I look at the tangent between C1 and C2, then I'll add the beta, which is controlling the tangent of this. So this is going to be bounded by this parameter kappa times the distance between C1 and C2. Okay, the kappa is supposed to be small. It's quite trivial to see that this delta quantity is always bounded by the distance. Okay, so the idea here is it's bounded by a small multiple of the distance. So then the conclusion, which I'm running out of space, I'll just fit it here, is that the angle between C1, C0, C2 is bounded by capital 1R. Okay, that's our limit. Okay, so what the hell does this mean? Right, okay, so first of all, this lemma is very elementary, it's just trigonometry, but it's obviously there's a lot of notation. We'll see, probably be able to do initial proof. But the important thing is to try and interpret it correctly. Okay? So remember, we're interested in a situation where all our circles in our collection are tangent, beta tangent to some fixed circle. That's kind of what we reduce to, right? A situation where, or at least there's many circles are tangent to a fixed circle. So here C0 is our fixed circle, and we have two circles in our collection which are both tangent to our fixed circle C0, okay? Now we have these other conditions, like I said, they're not too important, they just come by pigeonholing and what have you. Now the thing is, remember, we're really interested in having many tangent pairs. Okay? So let's say that not only is the C1, C2 tangent to the fixed circle C0, but C1 and C2 are tangent to one another. That's going to generate more tangent pairs, yeah? Well, what that tells us is that the angle has to be, of tangency has to be small. So that means that all the tangencies have to be lining up in a particular direction, which means we look like a clamshell. That's what it's saying. Okay. So it's quite easy to see this just by drawing pictures. So let's just go back to this picture. Here we have two circles, C1 and C2, that are tangent to C0, but the tangencies are in different directions. But then we see C1 and C2 themselves are very far from being tangent. They're passing through one another. Right? So that's kind of the negation of the statement somehow. Make sense? Okay. So in general, I'm going to try to avoid doing proofs of things that involve trigonometry, based solely on trigonometry, whenever I can give some kind of intuition for the numerology. But in this case, I'll make an exception. I will go through the proof, even though it's pretty elementary. But hopefully it's not. Yeah.
If C1 and C2 if C1 and C2 have a different direction, can they like be out of tangent as well?
Out of tangent. Yes, of course, it's a good. Yes, that can easily happen, right?
Right.
But we're never in a situation where we have out of tangencies, and that's because our centers are localized to a small q, and our radius have length 1, so they can never be far enough apart to give an out of tangency. That's from localization of the operator. So that's why we want to work with radii about 1. Does that make sense? So the centers always lie in the unit q, right? Unit square. and the radii at least one. So to have an outer tangent of C, you have to have the centres distance 2 apart, which is not possible in that cube. Okay. Does that make sense?
Yeah.
So yeah, so you're right, you can have an outer tangent, but we're excluding them. Okay. That's a good question. Any other questions? Okay. So the proof of this complicated looking lemma is based on the law of cosines. Right. Remember what that is. It's a long time since I was in high school. The law of cosines obviously is the generalization of Pythagorean theorem. So if we have three vectors x, y, and z, have a look at the difference between x and y squared. I can write that as the sum of the differences between y and x squared and z and x squared. So this holds the equality when the vectors form vertices of the right angle triangle, but in general we have this correction factor, which involves this angle alpha, where alpha is the angle between y minus x and z minus x. So in the right angle case, cos alpha is 0. Okay. So we can use this to obtain a quantified version of the triangle inequality. So what this says is the following. So with the same setup, we have these three vectors in R2. If we look at the difference distance between z and y, plus the difference between y and x, minus the difference between z and x. Okay. Now, by the triangle inequality, this is always non-negative. But we're going to do a quantified improvement over this. So it's always bounded by the distance between y and x times alpha squared, where alpha is that triangle we've seen before. Okay. So the proof is just going to use the law of cosines. So how do we see this? Well, I'm going to write out the law of cosines again. But I'm going to make the square here. We're going to have y minus x minus z minus x all squared. Then we're going to have to add the cross terms. And also the cross terms feature in this, this correction factor in the law of cosines, right? So now we can rearrange this and write as the difference of squares. So we have x minus y times x minus z times 2 times 1 minus cos alpha. Well, that's roughly alpha squared. Okay, because that's not cos. It's going to be roughly this difference of squares, which is z minus y squared minus this whole thing. Okay, so I'm going to write this as a, I'm going to factor out the difference of squares. And we're going to get z minus y minus x plus z minus x times z minus y plus y minus x minus z minus x. Okay? So this is the term we're looking for on the right-hand side, well, the left-hand side of the inequality. Because the thing comes from the... And for this guy, we can use the triangle inequality bounded from above. So in particular, that's right, we can bound z minus y by z minus x plus y minus x using the triangle inequality. This y minus x cancels with that. We get 2z minus x. But then the z minus x on this side cancels with the z minus x on this side. And then we're left with what we try and prove. Yeah. Did this quickly, but hopefully it makes some sense. Okay, so this inequality actually pretty useful in all this business, despite it being elementary. Okay, and then I'll finish off with the last couple of minutes proving the lemma. So remember, we're trying to prove, well, okay, I'm not going to go through the whole statement, but at the end of the day, we're trying to bound this angle. So this angle theta is the difference, is the angle between center x2, c2, and x1 is c1, and x0 is c0, and x1 is c1. Okay, so c1 is the circle in which we're measuring the angles. And so we can apply the quantified triangle inequality with this theta, and what this tells us is the difference between x1 and x2 times this angle theta squared is going to be bounded by the difference between x2 and x0 minus x1 minus x0 plus x2 minus x1. And now we want to bound these terms. So by hypothesis, this tangency between C0 and C1, which is equal to, well, we'll go to C0 and C2 first, which is equal to the difference between the centers and the difference between the radii. This less than beta, and similarly the C0, C1. And this tells us that if we look at x2 minus x0, that's going to be bounded above by the difference between the radii plus beta. And if we look at x1 minus x0, this is going to be bounded below by the difference between the radii minus beta. Okay? And then we just plug this in the formula. And so we get this right-hand side is going to be bounded by, okay, we've got R2 minus R0, bound the first term, plus beta, and then we subtract R1 minus R0, we get R2 minus R1. Oh, it's a bit weird because it should be, maybe I've done the ordering of this. I'm going to keep it anyway. We get the difference between the radii, and then we have the difference between the centers. Ah, no, that's right, sorry. And then we have these two betas. But this is just delta C1, C2, C beta. And because this is minus R1 minus R2, which is the absolute balance. And now we rearrange, that tells us that our angle is bounded by, our angle squared is bounded by, and the tangency divided by a distance. And now we apply our hypotheses. So we're assuming that this numerator is bounded by capital times the distance. And then we divide them by distance. So we get that. I did this very fast. No. Okay. But yeah, so just to recap what we've done in this lecture. So we started out by looking at these inner product parents, and we saw that they decay really quickly if the circles are transversal. From that, we're able to prove a good bound under the hypothesis that there are very few tangential pairs, and this isolates the tangential guys as the enemy. So then we noticed that there is one particular configuration, which is this shell configuration that produces many tangent pairs. And then this last lemma, we showed that somehow this clamshell configuration is the only configuration that produces many tangent pairs, because in that case, the tangencies all have to line up in a small angle, which is exactly what we're seeing here. Okay. So next time, we're going to start to analyze this clamshell configuration. So we're going to use a lot of geometric facts, but I think this was a bit of a failed experiment doing this trigonometry, rapid trigonometry at the end of the lecture. So I think I will try to reduce the computation, and we'll be able to see the other identities kind of more intuitively. Okay. Right. Okay. So thanks very much. I'll see you next time.
Thank you, Jonathan. So it's time for questions or comments.
I have a comment.
Yeah.
It seems like the analysis you're describing here is very precise. It's all these trigonometric arguments and so on.
Yeah.
So how robust do you think that these?
They're all pretty robust. I mean, they all.
So
I mean,
perturb the circle. I want to perturb.
Sub did it for this variable
coefficient.
Sub did all this stuff for variable coefficient operators, right? So
geometrically, these arguments carry through.
Yeah, yeah.
Okay, so can you? So for instance, if you take a convex curve, which is a finite type K, then we know that the circuit, then that maximal function is bound on LP if and only if P is bigger than K. That follows from Bourgain just by scaling, but I'm just wondering if these arguments.
Okay, yeah, I don't know how to.
Can these? We want to see that.
I haven't thought about that. Yeah, well, I haven't tried to do it. I mean, presumably it does, right? Because
yeah, I was just curious. I mean, I just wondered
well, as you say,
instead of seeing
it's a nice simple scaling argument, then I'm happy to use that. But as you say, since it's a nice scaling argument, maybe I'm happy just to do that rather.
Yeah. I was wondering if we can see sort of that why P has to be bigger than K sort of without scaling somehow. This is
yeah, well, you'll get configurations where you have high order of contact, right?
Right.
So that's going to be the enemy.
Tangency
so the scaling argument, sorry?
Tangency plus high order contact.
Yeah, so I guess I don't know how. Okay, maybe it is interesting. So then you want to isolate what configurations have high order contact, so that you can have high order contact in many different directions. So yeah. So there are controls over this kind of more explicitly in some recent work of Josh Saal.
Yeah, right. Okay. That's right.
Any other comments? Well, if not, then let us close this session and then we have lunch.